Hello, and welcome to TI Precision Labs series on inductive sensing. My name is Justin Beigel, and I'm an applications engineer in the current and position sensing product line. In this video, we will cover button applications using inductive sensors. The basic principles of inductive sensing have been covered in a previous video, so we won't go into too much detail of how the sensor works. For inductive touch buttons, we are detecting minor deflections in the metal target rather than the motion of the metal target. When a force is applied to the metal surface, a deflection is caused, changing the inductance of the sensor. For a button press to be detected, a threshold is set at a certain inductance and a button press signal is created when the threshold is crossed. This implementation can be used to replace any standard button. There are many advantages to using inductive touch as a button replacement. One of the bigger ones is being able to remove cutouts for standard buttons while also not needing to ground the surface like you would in capacitive sensing. This can make processes like waterproofing easier since there is no need to hermetically seal the button. It also makes it so the shape of the button can be changed for the design. Another benefit is being able to sense the actual force response of the button press. This allows inductive touch to work with gloves and can be immune to false button presses. To design an inductive touch sensor, there are many things that need to be considered. Starting with the mechanical structure of the button, this is the recommended stack-up for a button design. On the outside, the target, or metal surface, has the touch force applied to it. On the inside, the sensor is centered on the touch event to make sure the deflection is captured. The gap between the sensor and the metal is a critical component and will be covered more in depth in a little bit. In cases where the sensor coil is built on a flexible material, a stiffener is added to make sure the sensor coil does not flex when a touch force is applied. If the sensor is built on something like FR4, the stiffener is not necessary. Additionally, FR4 can be used as a stiffener if a flex PCB sensor is used. Lastly, a clamping force is applied to the area where the spacers are to ensure the deflection gets detected properly. For designs that do not have a metal conductive target on the outside, a metal film can be inserted into the stack-up between the surface and the sensor. This can be done to make materials such as plastic and glass usable for inductive sensing. The metal film will still deflect the same as the surface and provide an inductance shift similar to the normal metal target. I would again like to note that even though the stiffener is noted to be optional here, it is only optional in sensors that are built to be sturdy like FR4. Now that the general stack-up has been covered, here are some other key factors to take into consideration when designing a metal touch button. Now that the general stack-up has been covered, here are some other key factors to take into consideration when designing a metal touch button. For the target size, the area of the target needs to be big enough to cover the entirety of the sensor. Additionally, a target with at least 3 skin depths will produce a better inductance shift in the response. The sensor coil size is sometimes limited by the amount of space available for it in the application. The size of the coil is also a key factor in the inductance of the coil. In a racetrack style design, the effective diameter, or size of the sensor, is the smaller distance across the coil. Using a racetrack style will increase the target area, inductance, and series resistance of the coil compared to the circular counterpart. The increased inductance can become a benefit, especially in small space designs. Other things that impact the inductance are trace width, number of turns, and the thickness of the copper used. Finally, the distance between the sensor coil and the target determines how well of a response the button will get. If you remember from earlier, this is the space or the gap between the sensor and the target on the mechanical stack-up. As you can see from the graph here, keeping the target distance shorter than 20% of the sensor diameter results in the best sensitivity to a button press. There are a lot of variables when designing an inductive touch button, but there are also a wide variety of tools and resources available. While researching for this application, determining which part to use is a big portion of the work required and will impact the rest of the design process. The LDC Device Selection app note has information on all LDC devices and is a great tool for picking the right part. The LDC EVMs are great tools for evaluating for an application and can benefit from using one of the TI coil EVMs or a custom coil that reflects the final intended coil properties. The EVMs are also great tools when prototyping any design. There are app notes available that help cover the design for the sensor coil and target. Additionally, the LDC calculator spreadsheet and FEM tools are great for designing or debugging a design and there is an app note available to help utilize the FEM tool. Lastly, if issues arise in the button application, there is an E2E forum where many problems have already been solved and a frequently asked questions page is established. We won't go in depth with all the resources, but we will quickly cover a design with the LDC calculator spreadsheet. The Excel calculation spreadsheet has inputs for various parameters of the sensor and will calculate the frequency, inductance, parallel resistance, and quality factor of the sensor coil with and without a target present. This spreadsheet has instructions embedded and will also warn a user if any value is out of range for the device selected at the top of the inputs. Here you can see the sensor design has been input with a 6mm circular coil with a 350 picofarad capacitor. We have chosen 9 turns per layer and are only doing a 2-layer design, while the trace width and spacings both have been selected to be 5 mils. Based on the inputs of the last slide, the sensor design gives a frequency of 8.43 MHz without any target present. You can also see that the target distance has an impact on the coil design. With a distance of 0.3 mm away from the coil, which happens to be 5% of the coil diameter, the frequency of the sensor increases to 13.815 MHz. We can also see the quality, or Q factor, for the coil design. Having a Q factor that is too high can lead to a sensor that is more susceptible to noise. As you can see from the results, our Q factor drops significantly when the metal target is added to our design and is at a good range for this application. This tool is great for designing a coil and making sure that it will work with the LDC. The actual values of the physical coil may vary due to manufacturing tolerances, but should be fairly close to the values from this calculator. Lastly, I want to mention that this tool has device-specific tabs. These tabs can give more details about the coil design for each device, and some even give recommended register settings to get started with the design. Now that the design of a button has been covered, there are a few data processing things I want to touch on, the first being baseline tracking. The frequency of a sensor can change as the temperature increases, and this effect can cause the data to pass the button threshold even though no button has been added. This will result in invalid button press events unless some form of baseline tracking is implemented. Baseline tracking accounts for slow changes in the sensor and can even negate any dents that are created in the touch surface. Some LDC devices can implement this tracking feature on their own and output a digital button press, while others might just deliver the raw data. A simple baseline tracking works like a slow-moving average. As the temperature slowly increases, the average increases with it. But when a button press happens, the data shifts very quickly and the moving average doesn't keep up. This concept is shown on the right. As you can see, the baseline increases, which impacts the button press data. But once the button was released, the baseline was negative and took faster steps to get back to normal due to a fast recovery tracking implementation. This basically means that when the data is negative, the moving average will change its weighting to get back to zero faster. Baseline tracking works by changing the baseline value for the LDC measurement, but another approach is to have a variable threshold. This applies the same concept but to a different variable when doing data processing. For a touch button, a gain factor can be used to change the sensitivity of the button press for designs that have more stiffness. A higher gain factor can also decrease the effective resolution of the system, but would allow for a smaller deflection to be detected as a button press. The ability to control this is implemented in some of the LDCs that TI offers, but can also be implemented when processing raw data with a microcontroller. Another approach to change the sensitivity is to adjust the threshold of the button press to accomplish the same goal. That concludes this video. Thank you for watching. For more information on inductive sensing, please visit our TI product page.